Welcome back, everybody. The topic today, and this is the last session before the break, is to discuss some of the parallelization, but we're also going to discuss vectorization strategies. And we're also going to take an overview look at project number 1. And then we are going also to point to possible directions for project number 2. So for many of you, the topics today may be pretty well known because some of you are taking a course at the University of Oslo, which is called IN 4200, which actually deals with high performance computing. Now, the material which I will cover today deals more with the strategies on how to speed up our code and why we would use parallelization libraries like message passing interface or OpenMP. And then we're also going to spend some time on vectorization and how we can actually, with very simple means, speed up our codes. Now, this part is more tailored to those of you who write programs in C++, Fortran, or similar, what we normally call low-level languages, mean closer to machine language. While for Python users, there's been a kind of, until recently, there's been a kind of lack of support for using MPI and OpenMP directly. So we're coming back to some of these issues. But what I wanted to take the opportunity to first is actually to try to point out to the things which we have in project number 1 and how we can link that with the coming projects after the Easter break, which is pretty imminent now. I should also state that when it comes to deadlines, we tend always to be pretty flexible. We put a deadline to March the 31st. However, if you are delayed, and this can often happen when we are dealing with large program development, there may be queues at the high performance computing facilities. There may be other things which happen in the last moment. So we're always flexible with the deadlines. So if you need a little bit more time, please just let us know. Okay, so I just wanted to quickly go through some of the basic points which we have in project number 1 and how these can be reused in project number 2. So let me just bring this up here. So if we look at the project number 1, there are some key ingredients which we have emphasized. And one of the reasons why we have used Monte Carlo methods is that sometimes it's felt as a method which has a lower mathematical threshold for getting started. If you look at many of the other many-body methods like Hartree-Fock theory, copper cluster theory, large-scale diagonalization, and so on, there is often a higher threshold for getting started and start producing results. So what we have gone through is the Monte Carlo Markov chain machinery. So this is what you have been implementing, Markov chain, in order to simulate a physical system, which also means that since this is a process, the Markov chain process, where we use Monte Carlo methods to pick randomly new suggestions for positions or configurations or whatever we might call it, we use then this machinery, the stochastic machinery, to generate new events. It takes normally a little bit of time before you reach the most likely state. So this is normally called a burn-in time. And every time we suggest a new configuration, we have a sampling rule, which in this case is, in our case, is given by the Metropolis-Hastings algorithm. So this is the Metropolis-Hastings. And we have encountered topics like importance sampling. So this implementing the Metropolis-Hastings algorithm normally means that we deal with importance sampling. So that's an important element which we have added to the codes. And this form basically the first part of the project. We have been looking at implementing a bosonic system. A boson trial wave function. Trial wave function with and without an interaction. And one of the measures which we have used in order to study whether the interaction plays an important role or not is one, to calculate the energy of the system, and two, to calculate the so-called one-body densities. So the one-body density is a very nice way by which we can display whether there is a large deviation from the non-interacting one-body density and the one which is extracted from an interacting many-body system. So we've been implementing this boson trial wave function. We have calculated the energy for many particles in 1, 2, and 3 dimensions. Energy. So these are the kind of quantities which we have tried to calculate. And then we also looked at the one-body density. So the energy is obviously unobservable. The one-body density is a purely theoretical construction, but you can relate that one to, for instance, for charge system, to the charge density of a system. So there's a possibility to actually relate these one-body densities to experimental observables. The energy is unobservable, whereas the one-body density is a theoretical construction which allows us to assess the importance of correlations when we compare the interacting case with a non-interacting case. And remember now that the non-interacting case may not be representative of a physical reality. That's also a theoretical model which we have designed. Now, this is the Monte Carlo Markov chain machinery. And what we have also looked at is optimization methods. Since we have a set of parameters which we want to optimize. And in project number 1, we can actually live happily with the plane gradient descent. So GD is one of the, or gradient descent is one of the standard methods which we can use. And one of the reasons why we implement the gradient descent is that to calculate the second derivative of the energy with respect to the variational parameters is computationally expensive and is also prone to large statistical errors because we have to calculate many more integrals than we do with the second derivative of the first derivative of the energy. We also have stochastic gradient descent and other methods. We encountered also something which is called the steepest descent, etc., etc. But for this specific case, the standard gradient descent is more than enough, and a gradient descent with momentum is a method which basically does the job as long as we can fine-tune different learning rates. So these optimization methods, they serve to find the optimal parameters. Then what we have is resampling methods. And in this case, this is a typical post-analysis. So this is an analysis which we make after we have run the large production run. And you have code examples from the lectures last week and the week before. And the method which we normally recommend using in this specific case is the blocking method, which is a method which is tailored to data sets with many, many samples. If you're having few samples, then people often tend to use the bootstrap method in order to get an accurate estimate or a good estimate of the standard deviation. Estimate of this variance. And when you have the variance, you also have the standard deviation. And ST dev, standard deviation. And finally, and this is a topic which many of you actually have studied, we enter into the high performance computing domain. So this is unfortunately a topic which we cover right before the deadline, high performance computing. So that's a little bit bad timing. But since many of you, what has happened in the last years is that quite many of you have actually taken a course like the IN 4200. So you're pretty familiar with these topics. But today we are going to discuss things like vectorization. We're also going to look at MPI. And the thing with Monte Carlo calculations is that they are embarrassingly trivial to parallelize. So MPI is something which can easily be implemented without too much hassle. There's not much communication. And then we have OpenMP. So MPI can be used on both distributed and shared memory. So distributed memory. And shared memory. Whereas OpenMP works basically on shared memory. So shared memory is something you can think of as your own laptop, where all processes share the same memory. When you have a distributed memory, you could have a farm of PCs, and you can then distribute memory across all these PCs. And then you need also communication between the different PCs or nodes which you have in a high-performance computing at a high-performance computing facility. But you can also have huge supercomputers where you have just shared memory. So these are the kind of common architecture which you will find in high-performance computing centers is normally that of a distributed memory. So you have a farm of PCs which can easily be upgraded with new software. You can add more memory to them, etc., etc., etc. So these are the type of strategies which we often end up with dealing. For the Monte Carlo calculations, life is pretty simple in the sense that we don't have much memory which is needed, and the processes can be run both on shared memory without any problems and also on distributed memory. And at the end, we just collect the data from the different processes, and that gives our total data set from which we then calculate expectation values. So the high-performance computing part, when we deal with these kind of topics, the Monte Carlo calculations, they are, as I said, embarrassingly trivial to parallelize. We actually need just only some few statements in order to parallelize the code. So essentially what we are doing is to parallelize an integration. And if you think of an integral, you can slice it in different parts, and each part can be run independently by different processes. So it's pretty trivial to actually distribute the processes across machines, and there is essentially no wasted time on communication between processes. You just submit the job and you scatter these to different processes, and then at the end there is one process which is the main process, which then collects the data from all the other processes. This had earlier the unfortunate naming master-slave approach, which is actually not a very good wording for it. So I normally will label these as the main process and then all the other computational processes which go in parallel. Okay, so but before we move on and go back to the topic on vectorization, which is also an important one, in particular because we can have a speed up of a factor 2 to 3 or even more if we vectorize our code without doing very much. So let's, before we do that, let's point a little bit to project number 2 here. And I'm doing this because I would like you to think a little bit about what kind of paths you're interested in, so that when we meet after the Easter break, we can then have a more dedicated discussion where we can even split in groups, and each group works on its own dedicated project. So one of the standard follow-ups which we've had is to extend project 1 to include fermions. P1 to include fermions. So that means that you need another trial wave function. And for the fermionic case, what you would need to implement then would be an ansatz, which is not given by the product of the single particle states. And in order to obey symmetry, this leads to something which is called a permanent. You need to actually deal with a determinant, which is the way you include the anti-symmetry. So that creates some technicalities which need to be addressed properly. So this is one possible path for project number one. So you would actually reuse essentially everything which you have in project one, but change in P1, but change trial wave function. So if you're interested in fermionic systems, this is a very, how to say, straightforward extension, but there are technicalities with implementing in an efficient way a anti-symmetric wave function ansatz. So that's the main and major technicality there which you would encounter. Now, the variant which has been very popular with many people has actually been to deal with neural networks, deep learning. So that means that the trial wave function is now replaced by a neural network. And in previous years, we have used a so-called generative deep learning method, which is called restricted Boltzmann machines. This year, we thought we could deal alternatively with a standard neural network or a Boltzmann machine, and that depends on you guys and what kind of interests you have. But the path which I would propose then is that we actually extend, and this is actually extending project one, so we can keep everything which we have in project one by replacing the trial wave function with a neural network, and feed into the network some of the basic physics information. Now, there are actually online several libraries already which can be accessed, and there's a lot of material in Python here, and topics like automatic differentiation, etc., are very useful topics to include in the development of such a code. So this is one possible additional path. Then what we know is that there are many of you who come from material science and condensed matter physics. And in that case, one of the projects which we have been looking at is to look at the dynamics. So this breaks with the project one. There is little overlap between this and project one, and this deals with time-dependent methods. Time-dependent, and we focus on mean field methods. And in this particular case, we are looking at a mean field method, which is called Hartree-Fock theory. But if somebody is more interested in density functional theory, this is also a possibility. But we would normally recommend to deal with this Hartree-Fock theory, because that has a lower threshold for getting started and actually developing your own codes independently. Because with DFT, there is a lot of machinery which has been developed, and there is a slightly higher learning threshold for getting started. So this is something which falls under the topic of dynamics of many-body system. And we are going to look at the system of quantum dots here in one dimension in order to be able to finish in time. At the same time, there are several scientific articles which we can reproduce in this connection. So the time-dependent mean field approaches is something which could form the basis for project number two. That will be independent of what has been done in project one. So the first two alternatives which you see here, this one and that one, they actually are examples of projects where we actually reuse project number one. So basically everything you have developed in project one, the only thing you need to do now is to change the trial wave functions. And for the deep learning approach, what I would suggest is that we stay with bosonic systems. We can also extend this to fermionic systems if that is of interest, but that would require a little bit more labor. Or that we can have several people working on this variant one, this one, or this variant here together. So we can have somebody who looks at the implementation of a fermionic trial wave function, and then we can have somebody who actually deals with the implementation of a neural network. And then one can merge the two and have one common final project where one has actually been able to address much more. So that's also a possibility, but that requires collaborations more across groups. Then the final one, which we normally have presented, is one which deals with many-body methods. This is also a project which does not overlap with project one. So it means that you would have to enter different many-body theories, and we normally recommend this one if you have taken a course like Physics 4480. And in that case, we have many-body methods like copper cluster theory, many-body perturbation theory, MBPT, which stands for many-body perturbation theory, and we can have other approaches as well. And that depends on your scientific interests. So this is a topic which we normally don't recommend unless you have taken Physics 4480. We've had also alternatives which go more into the direction of quantum computing. But in this case, we normally recommend that you have studied topics from quantum computing, or that you are following in parallel a course which is called Physics 5129. It should be 549. Sorry, 5149. And we don't recommend this topic unless you have some familiarity with quantum computing. So this is also an option. And these options, which I've listed, the last three ones, are options which do not overlap well with project number one. So they can be seen as independent tracks where we can, depending on your interest, we can then form subgroups with people collaborating. And also we can have separate lectures for those of you who are interested in these methods. And then clearly, there is also space for suggestions from you. But obviously, the suggestion should fall within the aims and the topics of the course here. Any questions so far? Any ideas or inputs you would like to come up with before we move on to the topic of high-performance computing and how we can optimize our program, one, without too much pain, and two, with some additional instructions which can actually allow us to speed up and collect more data for Monte Carlo calculations. So the reason why I suggest this now, and we are going to repeat this after the break, is that we would like you to start thinking about what you would like to do in the last project. So any ideas, thoughts for projects, please feel free to voice yourself. You can unmute yourself or just keep thinking about it. So we are very flexible with topics, but we normally would like to suggest some common topics where several people can actually collaborate. With the time-dependent Hjorth-Jensen project, when we had that one last time, it was in 2021, and then we actually had 8 people collaborating on it. And then we just had a subgroup which discussed that project, and we had dedicated lectures for that specific subgroup. And in 2021, we also had a large subgroup of people. It was something like 10 people who were more interested in deep learning and solving the same problems which we have in project one with neural networks. Feel free to ask questions. Don't hesitate. Okay, there don't seem to be much questions now, but give this a thought and then send us an email so that after the break we can actually start discussing the different paths, and then have more productive group sessions for those who want to dive into one or two of these or one of these directions here. Okay, so I'm going to bring up the slides. So basically the rest of the day is going to be based on the slides here, and you can look up this material whenever you want. In the beginning here, what we have done is actually to present things which some of you are pretty familiar with, but this deals with vectorization and how we can measure code performance and discuss code performance. Then there are several examples with OpenMP and MPI, and then examples which are more also tailored to the Monte Carlo calculation. So keep in mind that message passing and OpenMP are libraries, and that the Monte Carlo project we deal with is, as I said, embarrassingly trivial to parallelize, because you are calculating a multidimensional integral, and this can just be sliced up in independent portions, and every portion can then be run in parallel by one specific process. However, when we now look at so this is dedicated very much to Fortran and C++ and these more kind of low-level programming languages. If you're thinking of Python, Python has a library now which is called JAX, J-A-X, which has really been streamlined for more high-performance computing. Python has also NumPy, which allows you to vectorize many of the operations on arrays like vectors and matrices. So that means that NumPy actually has wrapper functions to old Fortran functions, like those written in the library called LAPACK, Linear Algebra Package, and BLAS, which stands for Basic Linear Algebra Systems, which deal with topics like efficient matrix multiplication and matrix vector multiplications. Now, for those of you who program in C++, or if you are using Fortran and different Fortran compilers, the kind of standard compile options with no flags is just you having this -C option here. That means that what happens is that the code is translated to machine language as it stands. That means the way you have written the code, that is the way the instructions are translated. So the compiler is not trying to do anything fancy. Just keep that in mind. Now, depending on which architecture you are on, you may have better C++ compilers or the standard GCC compiler. If you have access, and there's a student license for Intel's C++ compilers, which then are normally replaced with ICC as the shorthand for the command for compiling and linking and producing an executable. And the standard options which you would typically use, which allows you to speed up without doing much code rewriting, are typically these options either O2 or OFAST or O3. So you would typically have to look up the compiler options. So if you're in a Unix-based system, this is just man C++, and that should give you the compiler options for the different compilers. But I guess this is something which is things which you basically have been doing. And this normally gives an automatic speed up almost of a factor of 2 to 3, and it vectorizes the code typically. And I'm going to say a little bit about what vectorization means. Now, in C++ and in Fortran, you have some additional tools on Unix/Linux-based systems. So you can have a profiling of your program and find out which functions create bottlenecks. That can be very useful. And this tool, which is called -PG here, this compiler flag, this can allows you to run your code afterwards, the executable, with this software, which is called gprof. And you also have other softwares where you can test memory usage, like Valgrind. And if you have other softwares you would like to recommend, please feel free to send this to all of us, or just send it to me, and I will send it out to everybody else. And these are typically options you can use when you study the program during your development stage in order to find possible bottlenecks. Just as an example, I used this tool some years ago, and we were able to speed up a program from something like 24 hours to less than half a minute. And the reason was that one of us had actually forgotten in the calculations of some recoupling coefficients that we were calculating the binomial again and again. So when we pre-calculated the binomials and stored them, then we reduced the computational time from close to 24 hours down to something like less than half a minute. And this kind of profiling tool then told us that most of the CPU cycles were spent in one specific function. And then we realized how stupid we had been. So that's a very useful tool. And when you have a large code, this is actually pretty useful to actually try. Another thing you can do is to look at debugging options. And we normally recommend doing that. But then you would have this for the no optimization flag, which is normally recommended. So it allows you, for instance, to trace if an array is properly allocated or not. And there are many, many other so-called compiler flags. And I invite you to take a look at the flags which follow a specific compiler. So for those of you who have Macs, I mean, the C++ variant is normally called CLang, or Clang, as many people call it. And then there are flags which, for instance, can catch integer overflow errors, which is also a very important thing to think of, because integers have a limited number of numbers which you can represent in a computer. So if you have 32 bits, you have something like a little bit more than 1 billion numbers. And if you would exceed that size, the compiler may compile the code without warnings. It will even run without warnings. This might happen. And it means that that number, which should not have been 0, is set to 0. And you simply continue calculating without any kind of warning. And this can obviously produce wrong results. So having in the development stage flags like this one, this applies to this specific compiler. Other compilers have other flags. So you would have to look up that in the man file. The standard one on Linux-based systems is the GNU C++ compiler. I've been using more the Intel compiler. There's a, as I said, free student version, there used to be. And also, since I have a Mac, an OS X operating system, I use this CLang compiler. And some of the options which you will see here actually tailor to that. Now, in general, there are some things which are useful to think of when you're writing a code. And one thing is to avoid, if you have a long do loop or for loop, is to avoid if tests or call to functions inside the loops. And we will come back to this. And it's particularly important for vectorization, because vectorization depends on the compiler knowing exactly what happens inside the loop. So if you have a break statement or an if statement, which may depend on loop variables, then the compiler doesn't know what to do and then doesn't vectorize the code. So vectorization is something which you get almost for free, but you need to do some thinking. And then clearly also avoid multiplication with constants inside loops. So some compilers are smart, and when you have these compiling options which go beyond no flags, that means beyond this 0 option, this could be option 1, 2, or 3, then typically the compiler tries to do something smart for you. And one of the smart things it tries to do is actually what is done here. So if you write a code like this, where you now run over the loop, so suppose n here is 1,000,000. Now, what you're doing now is that you're performing 1,000,000 unnecessary multiplications between two constants. So and that means that you have now, if you look at the floating point operation, if n is 1,000,000, you have 1,000,000 multiplications, 1,000,000 additions. So you have 2,000,000 floating point operations. And remember now that I'm also excluding memory lookups and memory writes. I'm not taking that into account when I look at floating point operations. We are coming back to that because this is something which we also need to think of. So when you're performing this operation, there's a memory lookup. So you have to fetch this element, and you have a memory write. So you have to write the new value of A in memory. Now, however, here you see now that we are performing 2,000,000 floating point operations if n is equal to 1,000,000. If you, on the other hand, perform this multiplication outside the loop, then you're simply performing 1,000,000 floating point operations because now there's only an addition. And we have left out memory lookups and memory writes. Furthermore, if you look at this statement here, this is also a pretty stupid statement because you're doing this memory lookups 1,000,000 times. And you're defining this E, which is now given by this K, where K is just a constant. This is something you would actually put outside the loop here. So your compiler, when you have these different compiler flags, that may do this for you, but it's not given. So you always have to check that the compiler, when you have a higher compiler flag than this is 0, that it actually gives you the same results as the code which you had written with and programmed and compiled without any compiler speed up options. So when you write the code like this and you have the compiler option 0, what the compiler does is that it translates line by line what you have written to machine instructions. So think of these things when you develop a program, because these are kind of cheap changes you can make, and they're also stupid bottlenecks, like us calculating these binomial factors again and again every time we call the function. And binomial factors are expensive to calculate. Any questions so far? I hope this is not too trivial. Now, if you now think of vectorization, this is one of the basic ingredients which we have and which we almost get for free with different types of compilers. And clearly, everything we want to do is to have shorter computation times, and we want to have larger simulation size. And the larger simulation size is something which is something we want in Monte Carlo calculations. As I said in the beginning of the semester, Monte Carlo calculations are extremely data greedy. The more data you have, the better it is, because we believe in the law of large numbers, which means that the more data we have, the closer we should get to the exact mean values. So we often deal with multiple processors, and the essence is actually to divide the entire computation evenly among different processes. So this is the old divide and conquer. And when it comes to types of software and hardware which we have, so the typical hardware, which is the modern parallel computers, they are so-called multi-instruction, multiple data machines. And they can execute different instruction streams in parallel on different data. So these kind of setups, they are basically obsolete nowadays. And like even the standard laptop now is a multi-instruction, multiple data machine, where you can run many threads in parallel, you have many cores, etc., etc. The ways to categorize many of these calculations is by shared memory and distributed memory. So the standard high-performance computing facilities, they are based on distributed memory. So the memory is scattered across all the different PCs we would have in a farm of PCs. Alternatively, you can just have one unique machine, which was not so uncommon many years ago. And you could have a company like Cray, which would deliver a huge machine with shared memory. And in shared memory, then the CPUs share the same address space, like on my laptop. So my laptop or traditional laptop, which you can buy almost in the supermarket nowadays, is a typical laptop which comes with 2 or 4 cores by default. And that means that these CPUs, they will share the memory which you have in your laptop, which is your global memory. And in a distributed memory, each CPU has its own memory here. And typically then the CPUs are connected by some network and may exchange messages. So the type of parallelism which we will deal with here is normally what is called task parallelism. That presents Monte Carlo calculations. There is no, you can think of this as just independent tasks. It means that you could now, and this is the standard setup, you let every process run independently the full Monte Carlo calculation. So if you then run this calculation with 10 million Monte Carlo cycles, you produce 10 million samples. And then you could have another 100 processes which run in parallel and independent of each other. And they are started with different seeds. So if you have 100 and you produce 10 million data in each, then you have produced 1 billion samples for your averages. And at the end, you would collect all this data. And then you would calculate the final averages. Now, what is more difficult is actually data parallelism, where you need communication and synchronization between processes. Like if you're solving partial differential equations, this is a typical challenge to distribute the update of the solution of differential equation across different processes as you move in time, if you have a time-dependent partial differential equation. So in our case, in this specific course, life is much, much simpler. And parallelization is something which we almost get for free. And as you will see, there are just some few instructions which we need to implement. So message passing is the kind of library type which is normally used. And this is the most common one, and normally allows for a rather efficient parallelization of your codes. So MPI stands for Message Passing Interface, and MPI is a library. It's a library which allows the operating system to communicate, set up the communication between the different processes which are running. And OpenMP is a similar one. So if you want to look at vectorization and get an understanding of what that is, there are some slides here which you can take a look at. And this is normally what I call the almost for free speed up of your code, without you not having to think much. And the reason for that is that basically all modern computers, they allow for vectorization, which you can use and perform several processes in parallel. So vectorization can be seen as a kind of parallelization. So if you now consider this example here, if you think of, if you look at this example here, and if the code is not vectorized, what happens then is that the compiler will just start with the first element and then just run through the loops here. So you would then have subsequent additions and blah, 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 and memory lookups and memory writes every time as you move the pointer I here. So the next point, you perform the same operation, etc., etc. With vectorization, you can perform chunks of these operations in parallel. And this can normally lead, depending on the type of variables you have, this can sometimes lead to a speed up of a factor of 4 without you having done much, which obviously is something we wouldn't disdain. So the idea between this is that you can operate on multiple data elements in one single instructions. And a typical register has something like 128 or twice as many floating point possibilities. So what happens then is that you, if you have, let's say, 4 floats or an integer, so you have an integer of 32 bits or float of 32 bits, not double precision, you can then accommodate in a 128-bit register, you can actually accommodate something like 4 operations simultaneously. If you have a double for 128-bit register, it means that you can perform operations on 2 doubles. And these registers can be larger than 128. But if you look at the example now, if you think of the code which we have here, this specific code here, if the code is not vectorized, and we have 128-bit registers to store a 32 bits floating point number, it means that there are actually 3 times 32 bits that are not used in this register. And we have actually unused space in the computations here. So if you look at the scalar operation, this type of operation here has, for n repeats, you have 1 load in address 1. We have 1 load here, and CI and BI are added to give AI, and then you store address AI in the address number 2 here. If you now look at a vectorized code, what happens in that case is that you can actually perform 4 operations simultaneously. So if you have a float or an integer of 32 bits, you can actually perform this operation here, and this operation, this one, and that one. And that's the same as you having a jump of I equal to 4 without you rewriting the code. So if you just write it with the first line here, and then you would have I equal to 1, then the vectorized version of the code will actually perform all these 4 operations simultaneously. But then clearly there cannot be any dependencies or any strange dependencies between the previous results and the next results. And we're going to see that after the break. So vectorization gives you a kind of free for almost no program rewrite, speed up of your code. So when you vectorize your code and you have a 128-bit register, you can actually perform 4 simultaneous operations. And this is a speed up which you actually get automatically. Now, there are, however, some bottlenecks which you should pay attention to. So if you look at the number of operations when this is vectorized, so for this n divided by 4 repeats, assuming floats, so 32 bits integers, you have 1 vector load for the C of I in the first address. You have 1 load for BI in address 2, and then you have CI and BI give this AI here. So you also have this memory writes and memory loads, which one also has to include in the final number of operations. Normally, when you set up the number of floating point operations, one is normally only thinking about additions, subtractions, multiplications, and divisions, eventually called to functions. Now, there is a simple test, and you can actually, if you click on the links here in the slides, you will get access to these codes. So all these links are clickable. And this is a simple example here where we run through a setup of just a simple array. And we perform a setup of, this is a plain C++ code, no fancy things at all. We define 3 arrays, and these vectors are then filled in with some mathematical functions, and that's it. And then we have a final vector addition at the end, and finally we calculate the norm here. And then there is also a final setup of the computational time, and we print out the final values. So we fill in the arrays here, and then we perform a vector addition And then finally, we perform a vector-vector multiplication here. And there's nothing fancy with this code here. And if you look at the kind of speed up you get, this is actually something which was done on my old Mac. I haven't updated this with the new Mac. And in this case, the calculations were done with the CLang compiler. So we have one option for no vectorization at all. You really specified that you have, in this case here with -O, there is no vectorization. And then you can have a vectorization and additional optimizations like a loop vectorization. And the speed up depends obviously on the size of the vectors. And here I run with up to 10 to the 7th elements. And you can typically see the time which is used for the calculation with and without a vectorization. So this is the no vectorization case, and this is the vectorization case. So what typically happens is that there is a speed up of roughly a factor of 1.5. But when you keep increasing this type of operations here, what happens is that you reach a larger set of matrix elements. So that means that you're actually running outside of the typical memory, which you would have in fast memory. And then what happens in this case is that the vectorized part seems to be running seemingly slower than the vectorized part. So it's not given that you will get an automatic speed up. But when you compile and link with and without vectorization with this compiler, these are typical options you can have with vectorizations and without vectorization. You would have to look this up for the different types of compilers. And if you looked into the chat before the break, there's actually a notice from Daniel and Håkon, where they were able, by profiling, they were able to find a bottleneck in the code, which we have online, which has been developed by Morten Ledum and Øyvind as well. And the get position method from the particle.h file was returning copies of the position vector every core instead of just a reference. And they could actually then speed up the program with a factor of 70% roughly, which is quite impressive. So there are, with profiling, vectorization, and so on, there are some simple things which can be done in order to speed up the code. Now, there is a nice guide from Intel where one goes through the some of these kind of topics which can hinder efficient vectorization. So one topic is that the loop counter, an important criteria is that actually that the loop counter is known at the entry of the loop, so you know how many loops you want to perform. Not all the loops can actually be vectorized. Now, a cosine function is the way it's tailored in most compilers is that's already vectorized. So even if you're calling a function here, a function like cosine, the exponential, basically all the intrinsic function, they are highly vectorized. So that means that this code here is actually a code which can be vectorized. And if you're using NumPy does this vectorization for you automatically. And you will clearly see a clear difference if you calculate this function here, or this array, with and without NumPy. There is a considerable speed up for those of you who use Python if you use NumPy. So if you have exit statements, then you may have problems. So a loop like this one is an example of a loop which cannot be vectorized. So you should avoid this kind of loop termination conditions and opt for single entry loop variable. The lower and upper bounds have to be kept fixed within the loop. So here the compiler does not know when this will break. And that means that it will then not vectorize that specific loop which you have. So these are things to think of when you're setting up your loops. And typically a loop should be written in such a way that you don't have if statements or calls to functions, because if these functions are not within those which can be vectorized, the compiler doesn't know what it should do. So a switch statement leads also to non-vectorizable loop, since different statements cannot branch properly. And the following code can, however, be vectorized, since the if statement is implemented as a kind of masked assignment. So these operations which you see here can actually be performed for all data elements, but only those data elements which the mask evaluates as true are actually stored. In general, and this is a kind of a general rule, if you can, you should avoid switch, goto, or return statements or if constructs that cannot be treated as normally what's called a masked state assignment. And this is what typically be a kind of masked assignment here. So this type of assignments are in general things you should try to avoid if you want to have an automatic vectorization. Keep also in mind that loops are vectorized so that the inner loop is the one which is vectorized. This has importance when you are dealing with, let's say, matrices. So the exception is obviously if an original loop is transformed into an inner loop as a result of compiler optimizations. So the compiler may try, if it knows the limits here of the loops, it may actually interchange it so that you have more iterations or more loops which are performed in the inner loop than in the outer loop. So if you have a variable m here instead of n, and m is 10,000, you should normally perform the inner loop should be the one which has the most looping variables or the largest looping variable, whereas the outer loop should be the one with the smallest number of looping variables. The compiler may change these for you, so be careful with that. Calls to programmer-defined functions, they often ruin vectorizations. However, if you're using intrinsic functions like sine, cosine, etc., they are normally efficiently vectorized. So this is an example of a loop which would be vectorized. Similarly, in C++, you know that you have this option with inline functions, which are defined by the programmer. They allow for vectorization, since the function statements are glued into the actual place where the function is called. Then there are some other kind of small bottlenecks you should think of. So a vectorization changes the order of operations inside a loop. A so-called read after write statement with an explicit flow dependency, like the one you see here. So there is an explicit dependence on the previous result. This is something which cannot be vectorized. So this is the example of this code is an example of a flow dependency, and it would actually result in wrong numerical results if it's vectorized. So for a scalar operations like this one, the value which you have the previous value computed during iteration is loaded into the right-hand side, and the results are fine. So if you have a scalar operation, no vectorizations. In a vector mode, however, with a vector length of 4, these values, A0, A1, A2, and A3 from the previous loop will be loaded into the right-hand side and produce wrong results. That is, when you do this now, you see that A1 depends on A0, A2 depends on A1, but A2 here, if you're vectorizing it, it means that A1 should have been updated, but it would not be the case because it will take the old value of A1. So these are also other types of bottlenecks which you need to think of. In case you cannot do anything with it, okay, then you have to live without a loop which can be vectorized. If you have a so-called write after read statements, they can actually be vectorized, and it's easy to see that. If you're parallelizing, there may be problems with such a code. So dependencies inside the loops are things which you need to think carefully about. But as a kind of rule of thumb, what you can say is that if you want this efficient vectorization, you should avoid having if, switch to, and go to statements, return statements, or similar statement depending on the programming language, which allows you to jump or break out of the loop. So if you can avoid dependencies on previous results, then these are loops which can be automatically vectorized. It's also worth to keep in mind, if you're using C++, that when you're dealing with arrays, you should avoid what's normally called memory stride, because that slows down the computations. So in C++, the way you access matrix elements is by starting from rows and then going through the columns. If you are programming in Fortran, it's the opposite. So Fortran has matrices which are column-based, whereas C++ has row-based. And that means that if you, when you access the matrix elements, you should then try to follow the way the programming language sets up the access to and memory fetches of specific matrix elements. So that means that the pointer moves in C++ along a row. So if you have row 1, it takes elements A11 and then 1, 2, 1, 3. So it moves along the columns and then it moves to the next row. If you program this, if you interchange I and J here, then it's going to jump in memory. And jumps in memory leads to something which is called memory stride. And that leads normally to a considerable slowdown in efficiency. So one thing is the number of floating point operations. The other one is also the way you fetch elements in memory. So there are some memory topics to think of. And I wanted to mention this before we move on to parallelization. So the typical main memory contains a data program. So cache memory contains a copy of the main memory data. This cache memory, which is smaller, is faster, but consumes more space and power. And it is normally assumed to be much faster than main memory. This is cache. So if you can do all your calculations in cache, this is normally the preferred option. And then you have registers, which we have already mentioned. They contain working data only. So if you're vectorizing, then it would just deal with the data which are at that present moment acting upon. So modern CPUs perform most of all operations only on data in registers. And multiple cache memories contain a copy of the main memory data. And cache items accessed by their address, they are accessed by their address in main memory. And L1 cache, so cache is actually divided in different types of cache. And if you can fit everything into the fastest one, that is the one which is preferable, but that's also the one with the least capacity. And loads and stores to memory are things which you should also think of. Now, for project number 1, this is not so important because project number 1, and this is one of the benefits of Monte Carlo methods, there is not much memory requirement, except for you storing the correlated, the positions of the particles when you're updating the correlated part of the wave function. So if you have, on the other hand, large memory requirements and large matrices you're dealing with, this is something to think of. Most communication is normally carried out in chunks and blocks of bytes of data that move together. And when you look at the memory hierarchy, data moves between memory and cache and between different levels of cache. And these lines are typically, they move in groups called lines. They typically contain a certain number of bytes. So typically this is up to 8 to 16 double variables, double precision words. Many of these performance features are not captured in most programming languages, and this is a little bit unfortunate. So when we measure performance, one of the things which we often would do is actually just to measure or start the clock, and then write a start clock here and finish clock. and then we calculate the time which has been used by taking the difference between the final and the start time, and then we divide this by the clocks per second. So if you look at this loop here, you may ask, this does look pretty innocuous. There can't be anything wrong with that one. But if you think a little bit more, the times are not infinitely accurate. So there is a granularity for the clock. So there's actually a minimum time that they can measure. So that can actually fool you in the sense that you have a good speed up. That's actually something which would then be related to the granularity of the clock. There's an error in time measurement, even if everything is perfect, and that may be the size of this granularity. You should always know what that granularity is. And you should also ensure that your measurement is for a long enough time, which means that if you go back to this code, if you have a very short time for the measurement, so if this loop is very small, you may actually be, deceived by the performance time, because sometimes most of the code may still not be in memory. There may be time which is needed to load the code, etc., etc. So there may be operating system constraints which kick in. And these are sometimes things you cannot control fully, because the operating system is doing many operations in the background, and you may not have control over all the operations which are running. So your program may actually be delayed simply due to the operating system being busy with other things. So when you now are clocking the time used by a program, you should run it long enough so that you that the time which the operating system is delaying your code is just a tiny fraction of the total time. When a code is executed, the assumption which we make then is actually that the code starts immediately. But it may still be on disk and not even be read into memory. The data may be slow in memory rather than fast. And sometimes you don't have a total control over that. And multiple tests are often necessary to ensure that cold starts effects are not present. So these are typically called cold starts. And special efforts often required to ensure that that the data in the intended part of them is actually in the intended part of the memory hierarchy. So there are several small such bottlenecks which we often don't control properly. So that means that when you run the code and you do the timing, you should think of this as a measurement. So actually also, if there's another thing, if the result of a computation is not used, the compiler may actually eliminate that part of the code, and that will can often lead to a performance which is pretty good. It may even eliminate some parts of the codes so that performance looks plausible. So what you should make sure when you run the code is that the parts you want to clock, that all the parts are actually being used. Because sometimes the compiler may skip parts of the code which is not being used when you're running the code. And that may give you a false impression about the performance. And as I said, you should view this as an experiment. So that means that you should make multiple tests. And this is something which you normally do in the development phase. And then by making the multiple tests, and you calculate at the end the average of all the tests, and that gives you an average performance. There are other activities which share your processors, or the operating system may be doing things, and some parts of the hardware do not always perform with exactly the same performance. And that is why you should think of your code and the running of your code and the timing of it. You should think that as a numerical experiment. And that's why you should take averages. So when we are measuring performance, accurate, reproducible performance measurement is very hard. You have to think carefully about what you want to measure and what it is and how representative it is. So these are just some things to think of when you're measuring the performance of your code. So some of you may have met an algorithm which is called the Thomas algorithm for linear algebra equations. So this is a very, if you have a tridiagonal matrix, instead of doing a standard matrix inversion, you can actually solve a linear algebra problem, set of equations, by an algorithm which only needs n floating point operations, where n is the dimensionality of the vectors along the diagonal. So the matrix is originally an n times n, but there are many zeros in the matrix. So this is a very sparse matrix with only elements along the diagonal and below and above the diagonal. So this is a matrix which, if there's a matrix of dimensionality n times n or m times m here, then you have 3 times m memory requirements, because you need to store only 3 vectors here, one for the the matrix elements above the diagonal, 1 vector for those below, and 1 for the diagonal. Now this is a code which you can actually implement easily. So you would have a forward substitution. This is actually Gaussian elimination, but it's Gaussian elimination made simple. And when you're setting up the different stages of this algorithm with the forward and the backward substitution, which are standard in Gaussian elimination, this Thomas algorithm is a special case of Gaussian elimination adapted to this specific case. So what you would get then, you would have something like a given number of memory reads, you would have a given number of memory writes, you have a given number of subtractions, and a given number of multiplications and a given number of divisions. So when many people think of performance, they're actually only thinking of the mathematical operations. But you should also think of the memory reads and the memory writes. So like here, we have 1 memory read, there's 1 memory read, another one here, and yet another one here. And then we have a memory write. In addition, we have a new memory read, new memory read here. So in total, if I done the calculations correctly, we have n-2 times 14 memory reads, and we have memory writes. So we have 1, 2, 3, 4 memory writes here, multiplied with n-2, which is the number of operations which we are performing. And then we have a set of divisions and subtractions and multiplications. So we have the total set of operations includes standard floating point operations and memory reads and memory writes. And these are things which we need to think of when we are setting up a code and we are measuring the performance here. So I'm going to skip this one. You can play around with some of these codes. If you click on the links here, you can actually try to play around. There's a link again, a matrix multiplication. It computes also the Frobenius norm. I'm not going to go through these examples here. So when we think of speed up, the simplest form of speed up measures the ratio of performance between 2 objects. So versions of the same code with different number of processors, that's a possibility. You can have a serial and vectorized version. And you could also try different programming languages and 2 algorithms which should then obviously compute the same result. So this is a typical example of you evaluating the possible speed up. So one of the simple things to evaluate is actually the speed up due to vectorization. And I normally recommend doing that. And then the key is actually choosing the correct baseline for comparisons. So if you use the serial versus vectorized example, then you should use the compiler provided vectorization. And the baseline is pretty simple then. You have the same code with vectorization turned off and on. So that's pretty simple to perform. For parallel applications, this is normally much harder because it depends on the choice of algorithm. It depends on the way you decompose the processes, the performance of baseline case, etc., etc. So this is something which may not be so trivial to assess properly. But for the vectorization, contra no vectorization, this is normally pretty trivial because you would just have the same code. You don't do anything with the code. You just rerun it with different compiler flags. For parallelization, it's actually more difficult. But for parallel speedup, there are some kind of baselines which you can follow. And the typical baseline, the speed up is now defined as the difference between the time you have for one processor divided by the time with using P processors. So there's always a question whether the speed up can be larger than P, which is the number of processors which you have. So that means that using P processor is more than P times faster than you just using one processor. This can actually happen. The speed of a processor can be greater than P if memory usage is optimal. This is something which can happen in Monte Carlo calculations where memory usage is often minimal. So if you have a memory, the case of a memory bound computation with M words of memory. So if this M divided by P fits into cache, while M does not, then the time to access memory will be different in the two cases. And T1 would use the main memory bandwidth, and TP uses the appropriate cache bandwidth. So this is something which can play a role when you have memory greedy processes and you're looking at speed up. Again, Monte Carlo calculations are actually pretty simple from that point of view. There is not much memory requirement. If you assume when you're studying speed up, you could assume that all parts of a code, almost all, are perfectly parallelizable. So you call that fraction for f. And then the remainder fraction, 1 minus f, cannot be parallelized at all. So there will always be fractions of your code which cannot be parallelized. In variational Monte Carlo calculations, it's essentially all parts of the code which can be parallelized. So that fraction f is actually close to 100%. And that is, there is work that takes time W on one processor, then a fraction f for that work will take time f, now W times f divided by P on P processor. And then you could ask, what is the maximum possible speed up as a function of f? So typically on one processor, you would have T1, so 1 minus f times the time plus f. So this is the time which you use. So just to remind you, this W here is now the work which is needed on a specific processor. So it means that the total work on one processor is given by this quantity W. On P processors, you have 1 minus f. This is the part which can be parallelized, plus f divided by W, multiplied with W divided by P. And that results in a speed up of T1 divided by TP, which is now given by this ratio here. So as P goes infinity, this term, which now contains a non-parallelized part, it goes to 0. And the maximum speed up is then getting close to 100%. So if you have all but one parallelizable, then the maximum speed up is actually pretty close to 100%. So the in a Monte Carlo calculation, what we will typically see then is that the speed up is pretty close to 100%. So if any non-parallel code slips into the application, the parallel performance is normally limited. And in many applications, simulations, the fraction of non-parallelizable code is normally pretty small. So these are things to think of when you're looking at the timing. And typically when you now run these calculations, you would often choose between MPI and OpenMP. So OpenMP is pretty easy to implement. You don't need to install MPI as a library. However, MPI is much more flexible in the sense that you can use it for both distributed memory and shared memory machines. So what I wanted to say something first is about the, so I'm not going to say everything here, but the, I just wanted to say quickly something about MPI. So typically you would have to install MPI, and there's a useful link here from the OpenMPI website. And you would typically compile with MPI CXX or MPI C++. If you're using Fortran, it's MPI F90. And then you would compile it with the MPI C++. And you would run it with the command MPI exec. And then you specify here the number of processes you want to run. And this is the name of the executable. So this is the way you would typically run MPI on your laptop or on a high-performance computing facility, which consists of a farm of PCs. If you're using OpenMP, for those of you who use Linux, this is automatically included. And you will simply have a compiler flag which says -f OpenMP. And if you're using OS X, there is actually a compiler flag option which is libOMP, libopenmp. And this is something for those of you who are OS X users. You could then just use brew to install libOMP here. And then you would compile your program, and then you can add more compiler flags. But the compiler flag you would add here would be -LOMP. Check this, whether this is the case for your compiler. Things may change. And depending on whether you have an M1 chip or not, there may be changes you would have to make. If you're installing MPI, I normally recommend to install that if you have a sudo apt-get on a Linux-based system, or if you're using Mac, an OS X system, it would be an OpenMPI here. And then you would simply run your code with 10 processes or 10 threads, where you would then simply specify the number of threads here. So there's also a very useful library for developing code. This is an integrated development environment, which is called Qt. And you would then have to add this to the process file, to the project file. You would have to add the specific instructions if you're using Qt as an integrated development environment. So message passing has been there for quite many years, and it's a library. So it's not a machine hardware, or it's not a machine specification. It's actually a library which needs to be installed. And it's a library which allows the operating system to set up communication between different program elements. So the basic, and I'm just going to set up some of the basic instructions. There are some basic commands which are called MPI init, MPI finalize. You need these. You need to set up how many processes participate in a given process. You need to specify which rank a given process has, and then you can send and reduce messages. Now, when we are doing Monte Carlo calculations, you can still use these, but I would normally recommend to use this MPI reduce, where you have one node which collects the results from all the other nodes. And I'm just going to end this with some simple examples, and you can click on all the links here and install them to your laptops. So MPI hello world is the simplest one. So this would run in parallel. So you need an MPI init, this initializes, and it has this which I think I've never been happy with, this kind of C++ way of defining the input arguments. So it takes the number of processes as arguments, and it takes the program code name as an argument, and then it sets up the communication size, the number of processes, and it tells a given process which rank it has in the hierarchy. For us, in a Monte Carlo calculation, this doesn't matter, because we can simply define one process to have rank 0, and that's normally defined as the main process, which then collects the data from all the other ones. And then we need to have an MPI finalized. So if you use MPI, you would need to have these 4 statements: MPI init, comSize, comRank, and finalize. These are simply needed. And if you go to one of the examples which we have here, I'm going to discuss the trapezoidal rule. And this is a typical example. If you click on the link here, you can get the full program. And in this specific case, the way you calculate this integral is actually to separate it in sub-integrals. And if you look at the program, what you would do now is to define a function you want to integrate. You have a trapezoidal rule. Then you define the final and initial points for the integral, the endpoints. You define the step size h, but then you define the local start point and the local endpoint for the subintervals. And each parallel process will actually compute the integral from local A to local B, producing a local sum. So if you move on a little bit, you have the standard initializations, which you need to set up. You can set up the time for the start. I set up the initial values. These can obviously be changed. So the interval goes from 0 to 1, and I have 1,000 integration points. And then I define the local number of integration points as the total number of integration points divided by the number of processes which I have. And make sure that this returns an integer. That's important. And then I define, so every process gets assigned by MPI a rank. So I define my local integral starting point and ending point in terms of the rank and the local number of points which I have. And this simply defines my integration limits. So local A is from the initial value to the one which defines the specific process. And then I have a local A and local B here. With that, I calculate the local sum. So every process produces this local sum. And then I have a function which is called MPI reduce. So that receives as input local sum from the trapezoidal rule. It sends that one to MPI reduce. MPI reduce has then an operation which is called MPI sum, where it sums all the local contributions and returns the total sum. And then we are simply transferring one variable. This could be an array as well. And then we have an MPI double, which is the type of variables which we transfer. And everything is now accumulated by process 0, which is now the main process. And what MPI reduce does is to take the contribution from all the processes. So you can think of your program running independently of each other on different processes. So every process has a copy of your program, and that is running on every process. You collect this data with the MPI reduce, and then this rank being 0 is the one which now writes the total sum. So you shouldn't let all the processes do that, because then you will get wrong results. And you can then produce the final time, and at the end you have MPI finalized. When it comes to the Monte Carlo calculation, you can think in the same way. So you can let simply all the processes run the Monte Carlo calculations independently of each other, and then have one process which then collects all the data. And that's basically how you would implement MPI with this specific case. I see I'm running out a little bit of time here. What I have is an example here on how you can do a Monte Carlo calculation for this is the 2-electron case, which we have been discussing. And this is a C++ program. And in this specific case, you will see now that in my loop here, this is the main program. I initialize my MPI with the number of processes and the rank and the number of Monte Carlo cycles. And then what I'm doing now is that only the main node reads in, or the main process reads from file. So there is no competing write and read to file. And then I broadcast to all the other processes from process 0, which is the main process. I communicate now the variables, which is a number of Monte Carlo samples, which every process is going to do here. And now I loop over the variational parameters. I produce, every process produces its local energy. So that's the local process energy squared, etc. And then I perform the Monte Carlo sampling. And then I use my MPI reduce here, which now receives my local process energy, and then also my local process energy squared. And then it simply computes a total energy by adding up. So that means that the parallelization here is done at the main level, in the main code. and where I simply call the Monte Carlo sampling for each process, and this is done independently. And then it simply collects the total energy now, which then is calculated by dividing by the total data we have divided by the total number of processes. And that gives us the final variance and the standard deviation as well. So this is a typical example on how you can implement the Monte Carlo calculation for project number 1. So using MPI. And normally I tend myself to use MPI because I often work on distributed memory machines. But you will find the similar examples with the OpenMP. And that should be the next slide. What happened here? Let me just see. Here we go. So the next part, and this is something which I will leave a little bit to you to go through. If you want to use OpenMP, and if you're using shared memory, this is also another possibility. And there are examples here as well on how you can use OpenMP to run a calculation in parallel. And you will find examples on how to do this for project number 1 as well. And also the calculation of an integral, like this trapezoidal rule. So parallelization in general is actually pretty straightforward for Monte Carlo calculations. We don't have big memory issues. So this is something which you can easily set up and run separately without too much hassle. So for project number 1, the parallelization part is something which allows us also to produce many more samples and at the same time run within decent times. So if you have a runtime of 1 hour for one process and you parallelize this on 10 processes, you can produce 10 times as much data within an hour. Your total CPU time is obviously 10 hours because you have 10 processes. So when you're running these calculations on a high performance facility, you're not charged 1 hour if you run 10 processes. You will be charged 10 hours. So the total time stays the same, except that you can do more in a shorter time. But the total time obviously adds up, and that is the total time which you're being charged for when you run everything on a high performance computing facility. So in a high performance computing facility, you would have a certain amount of CPU hours which are allocated to your project. And when you're beyond that, you would have to apply for more CPU hours. And in some cases, you don't get more CPU hours because there's a lot of pressure on the facilities. But in general, the parallelization for Monte Carlo methods, like the variational Monte Carlo calculation, which is essentially a stochastic integration of a multidimensional integral, this is something which can be trivially parallelized. And I hope this kind of discussions we had today with also the kind of bottlenecks and how you can vectorize and get a speed up almost for nothing without doing too much except having a right compiler flag. These are things you need to think of and have in your codes. So I'm going to stop the recording here, but feel free to ask questions and hang around, and we begin with the lab right afterwards. And Øyvind should be there if everything is fine. So I didn't say so much about MP, OpenMP, but there are lots of slides and material which should get you started with OpenMP.